Hello friends, here in this video we will see various types of stresses. Let us get started with it. Types of stresses. These types of stresses will determine that how much, or we can say what stress is acting on a particular material. That is, if we are able to identify how many types of stresses are there, then according to the direction of load given, we can understand a material is subjected to which kind of stress. So let us get started with this. For the types of stress, we have the first one called as tensile stress. Next, compressive stress. Then we have shear stress. After this, we have torsional shear stress. Next, we have crushing stress. Then we have bearing stress, and at last we have bending stress. So now, when we are studying design of machine elements or machine design, in that case we should know these 7 types of stresses, because once we understand the types of stresses, we can easily say by looking at the nature of the load that a material is subjected to which kind of stress. So I'll start the explanation one by one, starting with the first one, that is tensile stress. Now, in order to explain tensile stress, I'll first draw a diagram. Here I can say that we are having a rod. Now if I draw the axis for it, here this is the axis which is passing through the rod. Now I'll say that D is the diameter of this rod and L is the length of rod. Now, when I'm talking about tensile stress, then the load is also tensile in nature. Here I can say from this diagram that this arrow shows the direction that this rod is subjected to an upward force, and here the rod is subjected to downward force. So this becomes an action of pull type of loading. So here I can say this is the load denoted by P. So the value of load is same on both the sides, but their directions are different. So because of the action of this, what happens? It is similar to this example. Like if I have a pen here which I can consider as a rod, and when I am applying 2 forces which will try to pull this pen, that is, the first force will try to pull it upward and the second force will try to pull it downward. So when I am pulling this, there is tensile stress developed in this rod. So the same thing happens here, which I can write here, tensile stress, that because of pull type of loading, the stress developed in the material is called as tensile stress. So here I have an example that because of the pull type of loading, pulling of rod in both the directions, tensile stress is developed in the rod. Next, the second kind of stress, that is compressive stress. For compressive stress, again I will draw this diagram of the same rod having the same diameter D and length is L, and again the load will be passing through this axis. But now what will happen is that the direction of load, it will be reversed. Here the arrow would be pointing towards the rod as I have shown here. So now, as we can see from this example, that when there is a push type of load, what happens is compressive stress is developed inside the material. Like for example, this rod, I can consider it to be subjected to compressive stress, and in that case what happens is when I apply two forces, one from the upward and the other from the downward direction, because of the action of these two forces, this rod, I am pushing this, so it is subjected to compressive stress. So I can say that because of push type of loading, stress developed in the material is compressive stress. Now, important thing to note here is that both in case of tensile and compressive stress, the load is passing through the axis, and the area along which the load is acting, it is circular in section. So this area is called as cross section area, which I can draw it here. If we have the rod of diameter D, then this area of rod is pi by 4 D square, and this area is subjected to stress, so it is called as cross section area. So this was regarding tensile and compressive stress. Next we will see shear stress. For shear stress, again I will draw a simple diagram. Here I have one plate. Next, I have the second plate. Now, they are connected with the help of pins or rivets. Now here we have two plates. These two plates are connected by this joint which is at the center, and it is called as a rivet having diameter. I'll say that the diameter is D for this rivet. Now suppose on this top plate a force is acting towards left, I'll call it as P. Here this load on the top, it is acting actually towards right, it is not towards left. Towards left it is there for this plate which is at the bottom. Now we can see the directions. Bottom plate, to that the load is acting towards left, and for the top plate it is acting towards right. Now because of these two forces which are acting, what can happen is that the top and bottom plates, they can slide. Okay, since they are moving in the opposite directions, so there is a possibility that the plates, they can slide in their direction, and because of that the rivet can break at the junction. Now when the rivets they are breaking, I'll draw the shape how it will look like when it breaks. Here I can show the diagram. So we would be getting the rivets in two parts. Here like this. This is the section at which they are breaking. Now it is very much clear from this diagram that because of the action of these two opposite forces, the rivet breaks into two halves like this, and the action which is here, it is called as shearing action, and the load, as I can say, it is tangential to this area. Area is actually area of the circle, because here if I say that D is the diameter of the rivet, that is on both the sides. So here area which is resisting this load, that is pi by 4 into D square. So I can say that in case of shear stress, the load is tangential to the cross section area. As we have seen here, the load is parallel to this area, so I can say either it is parallel or tangential. Now see, shearing, as I have seen this case, it is of single shear. I can write down shearing may be single shear or double shear. See, if the rivet is breaking into two parts, that becomes a case of double shear, single shear. If it is breaking into three parts, then it becomes a case of double shear. In that case, we would be having 4 pairs of area, and for that, suppose I will draw the diagram for double shear. Here also we would be having number of plates. Here I have 3 plates, as I can see in this diagram. We have 3 plates, and the load which is acting for the topmost plate, it is towards right, and even for the bottommost plate it is towards right, and for the middle plate the load is towards left. Now because of the action of these opposite forces, there are chances of the rivet breaking first at this junction and then it will break at this junction. So here we are getting 1, 2 and 3 surfaces of the rivet, that is, it is divided into 3 parts, and here we have 2 sets of areas, so it is a case of double shear. I hope shear stress is understood. Next is torsional shear stress. The next kind of stress which we are seeing, it is called as torsional shear stress. Now, for torsional shear stress, what happens is that suppose we have a shaft which is rotating inside a bearing. Now, here I have drawn a shaft and a bearing. Now, this shaft would be subjected to rotation, whereas this bearing, it is stationary. Now, what may happen is that because of this rotation, there are chances of the layers to, we can say, separate or slip. That is, each layer is subjected to some kind of shear stress. So what can happen is that, suppose this first layer, when the torque is acting, this is the torque which causes rotation. So because of that, there are chances to the first layer, suppose it may slip like this. and similarly the other layers, they would be subjected to stress. Because of that they would be slipping. So that is called as torsional shear stress. So here I'll write down the important points, that torsional shear stress is seen in members which are rotating. So torsional shear stress will be there in those members which are rotating, and because of that rotation there are chances of each of the layers for slipping. So this is a case of torsional shear stress. Next, after this we have crushing stress. Now, in crushing stress what happens is that, suppose for this also I draw a diagram like of a rivet, which we have seen in case of shear stress also. Now, again we have two plates. Here I can draw the section for them. Now here there are two plates which are subjected to loading in opposite direction. Now suppose, as we have seen in case of shear stress, instead of the rivet breaking, there can be a chance where, because of the load applied, this rivet, it can just crush. Crush means it is like, we can say, compression. It can crush here. So first of all, crushing stress, it is a localized stress acting on a member. So crushing stress, it is a localized stress acting on a member irrespective of the type of loading. So here I have written for crushing stress that it is a localized stress, means it will be acting only on those members, like for example which are pins, rivets, cotter, joints. Their crushing takes place more frequently. So here I can say that crushing is also called as local compression. And because of crushing, what can happen is the material, it cannot break, but it will be crushed into fine powders. Like for example, for a rivet, I can say that if I draw it separately here. Now, this rivet, it will not break, but its surface will be converted into fine powders like this. So this is an example of crushing. Like we have a concrete, and if we apply compressive force over concrete, and if that concrete, it just converts into fine powders, that is called as local crushing. So here the area which undergoes crushing is the projected area. Projected area means here the outer diameter and length, I can say that if the diameter of the rivet, it is D, and here if the length of the rivet is L, so therefore the area which is crushed, that crushing area is capital A is equal to, it would be pi d, that is circumference, multiplied by length. So this was regarding crushing stress. Next we have, after crushing, we have bearing stress. Now bearing stress, it is somewhat similar to crushing stress, but the difference is, in case of crushing, the members are stationary, like they are pin, there is cotter, we can say even bolts, nuts, they are subjected to crushing. But in case of bearing, the member, one of the members, they should rotate, or they are circular in cross section. So I can give you the example, like suppose we have a shaft, and over that if we have a bush, like the diagram I am drawing. Now I can say that this is a shaft, and here we have a bush. Now bush is that member which acts as a medium to connect shaft with the bearing. It means first we have a bearing, inside that we will be inserting a bush, and in that bush we will be inserting the shaft. Now what happens when this shaft is rotating, that is when the torque we provide, there are chances of this bush to get worn out, because the material of the bush is mostly soft. Like example, it can be rubber, it can be brass, gunmetal, bush, or we can say bronze, etc. So these are some of the common materials for the bush, whereas shaft, it is mostly made up of steel, which is harder as compared to the bush. So there are chances that because of continuous rotation of the shaft, this bush may get worn out, and the failure which is there, it is called as bearing failure. The stress which is developed in the bush, that would be called as bearing stress. So I can say that bearing stress, it is most frequently seen in those members which are continuously rotating. Like here I have given the example of a shaft rotating in a bush. Next, like crushing, since it was localized stress, crushing stress, even bearing stress is applicable only to the area which is in contact with the bush and shaft. So therefore, bearing area, capital A, it will be pi d, that is if I say d is the diameter of this shaft, that is small d is the diameter of the shaft. So pi d is the circumference over which this bush is in contact, and if the length of this bush is L, so pi d into L is the bearing area, and therefore bearing stress will be, it will be equal to bearing load, which I can denote it by W, upon bearing area, which is A. So this was regarding bearing stress. Now we have the last kind of stress, that is called as bending stress. Now bending stress is also simple. For this, suppose we have a beam which is simply supported at its two ends. I can call them as A and B. Length of the beam is capital L. Now because of the action of the central load, which is W, this beam, it can bend in such a way like this. It can bend in this manner. Similarly, if I have a cantilever beam, that is a beam which is fixed at one end and which is free at the other end, like this example. Again, if a load is acting at the free end of this cantilever beam, its length is capital L. Now, if the load is acting, this beam will be deflected downwards like this. So here we can see that both the beam, they are subjected to bending, and therefore the stress which is developed because of bending in the beam, that would be called as bending stress. So here I can say that bending stress, it is the stress developed in a member because of bending load. Next, bending stress is sigma B. Therefore, bending stress, it is denoted by sigma B, and it can be calculated. It can be calculated by using flexural formula, and that flexural formula is nothing but m upon I is equal to sigma B upon y, where m is the bending moment, I is the moment of inertia of the material of the beam, sigma B is the bending stress, and y is the distance at which maximum bending occurs. So here in this video we have seen various kinds of stresses. We had started with tensile stress, then we had seen first of all tensile stress, that was completed. Next we had seen compressive stress, then shear stress, we have seen torsional shear stress, crushing stress, bearing stress, and bending stress. So these 7 kinds of stresses are necessary to study the subject of design of machine elements. Without their knowledge, it is very much difficult to analyze how the failure takes place, what is the area, and how much is the stress stored in the member. So I hope everything is clear in this video.